We're going to be looking again at electrolytes. And so we have already done our demo or our lab, and so I just want to remind you that a strong electrolyte is going to deal with complete dissociation, and so that means that it is going to break apart completely into the cation and anion. Again, just two things it's going to break apart into, cation and anion. And so in our beaker, or when we draw this out, we should look for the cation, the anion, and then I'm going to put in parentheses here our water stuff, okay? So we're going to look for really the cation and anion, okay? For our incomplete dissociation, we're going to see that we are going to have a few particles break into cation and anion. Okay, so here they completely break apart. That means all of them break apart. Here it just says a few break apart. So what we're going to see here is we're going to see mostly the neutral compound. And then we're going to see the cation and the anion and our water that we're going to look for. Now our non-electrolyte or no dissociation is that is going to dissolve. So particles dissolve but do not break apart. And so in this we're going to see just the neutral compound. Okay. Requirements for dissociation. Again, first it has to be dissolved in water, meaning it has to be an aqueous solution. And again, the solute is what's dissolving in water. And then we have to look to see if it's a strong acid or ionic compound. So you have to look to see first if it's aqueous or a strong acid. Aqueous, or then you can look to see what type of chemical bond it is. Now I want us to take a look here real quick because we've got this lovely flow chart. And if you start up here, the first question wants to know, is it solid, liquid, gas, or is it aqueous? That's taking care of this first part here. If it's aqueous, then we have to know if it's ionic, covalent, or acid. And if it's ionic, it tells me to dissolve and that it completely dissociates, so break up into cation and anion. An acid, I have to know if it's strong or a weak acid. Well, my strong acids are right here, and my weak acids are going to be right here. Covalent, it says no dissociation. It still dissolves because it's aqueous, but there's no dissociation. And then it tells me to write the neutral compound in my beaker. If it were a solid, liquid, or gas, it's going to tell you to write the neutral compound. So this flow chart is going to tell us what to write or what to look for in our beakers when we draw them, okay? All right, so just a reminder, strong acids are going to be complete dissociators. Not necessarily going to have a lower pH. pH does not talk about the strength of your acids. For future reference, this is going to tell us that a K equilibrium constant is going to be greater than 1 or lies right. Lies to the product side. And our strong acids, there's 6 of them. They are HCl, HBr, HI. Those are our binary acids. All of them do my ride has hydraulics, okay? And then we have some of our oxy acids, which are going to be sulfuric, nitric, and perchloric I'm trying to write perchloric instead of HClO4. Sorry, that's an H, ClO4. All right, so the weak acids are going to have incomplete dissociation. That means when we talk about equilibrium in AP, their equilibrium is less than 1 and it lies left, or is reactant favored. Here we're going to see that we have double arrows. Here we're going to see a single arrow, okay? And any acid that's not strong is considered a weak acid, okay? So, dealing with that, that should help us out. For right now though, I have your strong acids listed down here, okay? And it even reminds you the H2SO4, only one H is going to come off at a time, okay? And so it reminds you over here as well on that. Okay, so in class we are going to talk about these relationships a little bit more, but I'd love to know what you think. What is your hypothesis that if you increase the moles of your solute, that means we're increasing our concentration? What do you think is going to happen here? I want you to come up with a guess. All right, we're going to look at this page. Okay, we're going to take a look at a couple of examples, and what we're going to do is we're going to draw what these things look like on the molecular level. And there are a few things that we need to know. First of all, if it's aqueous, AQ means it's in water. Now, water is both acidic and basic, and it dissociates. It does so incompletely, but water likes to go to hydronium and hydroxide. Again, incomplete dissociation, so that's why we have this double arrow. And so because we have water, it automatically goes to this. Not very much at all. The K value is very, very small, which means it lies very heavily here. Not even enough to make it conduct. You guys should have seen that in our lab or demo, that the control or pure water will not conduct electricity. And so it's a non-electrolyte. But in order for us to be the most correct, we want to show that the water's in there, okay? And so anytime we have something aqueous, we're going to draw and write in our water here, okay? All right, let's take a look at our first example. The first thing I'm going to do is it wants to know the name. MgCl2, well, I'm going to check first. It's a compound. It is ionic, which means that I'm using charges. So I'm going to name my cation, which is magnesium. Magnesium does not need a Roman numeral. And then after that, I have chloride. So this is magnesium chloride. Now, my type of electrolyte, I have to first look to see, what do I have? I have something aqueous, so it's aqueous. Is it ionic, covalent, or an acid? We said it was ionic. And in the beaker, it says to break up into cation and anion. Okay. It also tells me that it's dissolving in complete dissociation. So I know that I have complete dissociation here, which means it is a strong electrolyte. It tells me in my beaker that I should see a cation and an anion. Okay, so there are going to be some things we need to do. First of all, if it's aqueous, I'm going to draw in my waters. I'm going to put H2O. Now, it can go anywhere in the beaker, but I like to put them all in the same spot just to kind of help out. And I'm going to have H3O plus and OH minus. Again, all of these particles would be moving around. I'm just going to make up a number out in front here, like 12, because I'm going to have a ton of this versus not very much of my hydronium and hydroxide. Okay? All right. Next thing, I need to know my cation. Well, my cation would be magnesium, Mg, with its charge, Mg2+. And I'm going to switch my colors back for just a second. Let me find my my whiteout. We're going to be consistent here because my losers are green on my periodic table, right? So Mg2 plus. My anion, chloride, is Cl negative. All right, so how many Mgs do I have? I have one of them. How many Cls do I have? I have two of them. And so I'm going to draw in a second one. So I've got one Mg2 plus for every two Cl minuses. And that is going to show us that we have complete dissociation. So when I have magnesium chloride dissolved in water, I don't have MgCl2 bonded together. I have Mg2 plus ions floating around, and I have twice as many Cl minuses floating around. We saw that a little bit on our colligative properties lab. It had you find the number of particles, and then I told you, like for NaCl multiply by 2, and for MgNO3 2 multiply by 3, because we have 3 particles. So on this one, we would have had to multiply by 3 as well. All right, the next one, let's take a look. What type of compound? It's an acid, so that means I have to put acid at the end. Next, I'm going to use my ride has hydraulics, so hydrofluoric acid. All right, now I need to know about my dissociation, and so I know, first of all, it is aqueous. Because it's aqueous, you can go ahead and draw H3O plus and OH minus, and I don't know, let's do 29 waters. Again, I'm writing more waters down here than I do my ions, because that's what I should see the most of. Solid, liquid, gas, or aqueous? It is aqueous. Ionic, covalent, or acid? It is an acid. Is HF a strong or weak? Well, let me check. I don't see HF over here, so it must be weak. And in the beaker, it says neutral compound and cation and anion. So I saw incomplete dissociation. It's a weak acid. Don't cry about it, but it's a weak acid, which makes it a weak electrolyte. And I'm going to see my neutral compound. My neutral compound was HF. I'm going to see most of that. And then I'm going to see my cation and my anion. Well, my cation, again, my cation would be H plus, and my anion would be F minus. And again, we would see mostly HF floating around, but we would see some H plus and some F minus floating around. All right, let's take a look at the bottom ones here. Now, the bottom ones are a little different because here I'm going to give you the beaker, okay? So let's take a look here at what we see in the beaker. I see a cation with a positive charge. I see an anion with a negative charge. And I see something without a charge. I see water, which means that this is going to be AQ. Well, here it gave me my neutral compound. So that is HNO2. It already has things crisscrossed down here. HNO2, no visible charge. Well, in here I see my neutral compound. I see my cation. And I see my anion. And I did it backwards again, y'all. Cation. Anion. Cat. And then anion. Okay. Now, if I see the neutral compound, cation and anion, I should have incomplete dissociation, which means I have a weak electrolyte. If I look, I have an acid, and this would be a weak acid. Next, I just need to write the name. I know it's going to be an acid. NO2, that's nitrite. Sprite is delicious. So this is nitrous acid. Okay, we're going to do a few more examples in class, but I wanted you just to see a few things. See what you can do on some of these. before class tomorrow.